What would be a way to write concurrent programs in a fully declarative language? How could we design such a language so that in order to write a concurrent program, we would just say something like, this computation here needs to be concurrent. This data here needs to be used in a concurrent computation, and nothing more. Could we design a DSL, or domain-specific language, where this kind of code would be sufficient to have a safe and automatically parallel program? In this tutorial, I will attempt to derive such a language using a systematic reasoning from scratch, from first principles. I will then use this language as implemented by the chemist library, and we will run tests on very simple concurrent programs that I will use as examples. The first example would be to compute this expression, where obviously we can compute this and this in parallel and then multiply the results. How would we do that in Scala using a future? So we would first define the functions plus and times that would take, say, a tuple of two integers and return an integer, and they would add and multiply the parts of the tuple. Now we want to run the computations with the function plus in parallel on the two sets of its input values. And then we want to wait for the results to be available. In Scala we can use future to do that. And let me do it in this way. I will start by declaring future of these data values. And then I will combine them using map and zip in a computation. To those who are familiar with Scala futures, this is not necessarily the only way to do it, but this is equivalent. You could put just these function calls inside the future, but I choose to start from the beginning. If I declare data1 and data2 as future values, it's as if I have just declared them to be concurrent data, and then all the computations on this data is automatically concurrent and will be run in parallel when possible. This is the kind of language that I would like to design, where all I need to do is to declare that this part of the program is concurrent, and then I just do computations without explicitly saying what needs to be parallel with what and how many parallel processes need to be stopped and started and so on. Just for illustration, this is an equivalent way of writing this computation. I would like to emphasize that this does not ever mention anything about running things in parallel. That part is automatic. And that's the goal of what we're trying to do. We're trying to design a language or a domain-specific language for concurrent computations where, as much as possible, the concurrency is automatic and, of course, safe. So this test runs and verifies that we get the results. So this is so far standard Scala. The idea of declaring some data to be concurrent seems to be nice. So we start with concurrent data, and then all computations with that data are automatically concurrent, and they will run in parallel. Now we have done this using Scala's future, but actually this is a significant limitation for the power of our language. The reason for that is that a program written in this way must be an expression whose value is of type future. So it's a future valued expression, and such expressions can only implement a limited subclass of concurrent computations. Here are examples of what we cannot do using an expression of type future of something. For example, we cannot start a new process concurrently every time we get a new data item. We have to get a future once that future, so suppose we write some program, which is a for yield block, like this one, whose value is a future. This future at some point will be finished computing. At that point, we won't be able to process anything else. So we could not write an expression of this kind that would automatically start a new computation every time something happens. Another thing we cannot do with this kind of programs is to run several concurrent computations and select the one that completes first and discard all other computations. We cannot do this with futures because all we can do in the for yield block is sequence futures. We can run several of them and use their results. We cannot say, now out of x1 and x2, use the one here that finished first. There's no way of saying that. Another thing we cannot do with futures is to examine the current status of various computations that are now running in parallel, and using that information decide whether we want to start a new concurrent computation or not. So this would be a non-deterministic decision, and this is impossible to do with futures. The structure here is fixed. We cannot check the status of data 1. We can get its value waiting for it, but that's it. Now, certainly, there are other APIs that could implement some of this. So we could add, in other words, some ad hoc features to the future data type, so that, for instance, we can examine its status, whether this running future has been finished or not. We can do that, and Scala's standard library has such APIs, for instance, to examine the status. But other things would be harder to do with futures or impossible to do. So let us not try to add features to this primitive. Rather, let's find a better primitive or a better language. Consider the first question. How do we start a new process concurrently whenever a new data item becomes available or arrives? So let's say there is some mechanism whereby data becomes available. What does it mean? We don't know yet, but we need a mechanism like this, that a value somehow becomes available. So here we declared concurrent values and they are already available, but there must be some way in which they become available. We'll find out how that works, but assume that we have done it. How would we get a new process started concurrently every time a new data item arrives? Remember, our goal is to design a language that does not have explicit instructions for starting or stopping processes. We should just declare that certain computations are concurrent, and that should be enough. So it would be good if we could just declare some function to be concurrent, so to speak. And then this function should get evaluated automatically whenever its input values become available, in the sense that we need to still understand. So let's aim for that, so that we just declare a function, such as plus, to be concurrent. And then this plus of 1, 2, for instance, would be evaluated automatically whenever the tuple 1, 2 becomes available as concurrent data. So also, it makes sense then also to say that when this computation completes, we would expect that its result will also automatically become available as concurrent data in the same sense for any further computations that might be waiting for that value. Now, this seems to me now very similar to a description of the so-called functional reactive systems, or functional reactive programming, where new values are automatically processed by functions whose results are again automatically processed by further functions waiting for them. And there are several libraries that implement this functionality. I just give a few links that come to mind. And this is functional reactive programming, which is well and good for what it can do, but there's nothing that it can do in certain situations, because functional reactive programming is still limited. It is still too limited to be a general concurrency solution. The reason it's too limited for that is that functional reactive programming is equivalent to a stream graph. And a stream graph could be asynchronous, but still it is just a graph where data flows and gets modified or processed stage by stage. Many problems can be formulated like that, but not all problems can be. For example, selecting the computation that completes first is not something that you can formulate as a stream graph. A stream graph would process everything, or it will discard some values, but it will not discard values that arrived too late. And there are other things you cannot do. Again, some reactive systems, one of them, for instance, is Akka streams, and there are many other streams systems. They have features that allow you to do some of these things. But these features are ad hoc, they're difficult to use, and they're limited. They're not enough to be able to solve arbitrary concurrency problems. There are concurrency problems that cannot be expressed as an asynchronous stream graph. So rather than go into the functional reactive programming here, let's continue reasoning about these concepts of concurrent data and concurrent functions. Suppose we were able to design a concurrency language around these concepts. Then example 1, this computation of 1 plus 2 times 3 plus 4, would be rewritten as some code roughly like this. First, we declare the functions plus and times in some way as concurrent functions. Then we make tuples 1, 2, and 3, 4 somehow available as concurrent data. Then we also need to say somehow that these two tuples are inputs for the plus, and that there are two parallel runs of plus that need to be done for these two inputs. And also then we need to say somehow that the function times should get its input from the two results of these two runs of plus. So what would be the syntax for saying these things? Now, intuitively, if we were able to say these things, then I would say we have achieved a high degree of declarativeness. We just describe what we would want to do, and we declare that some of these things need to be concurrent. Everything else is done automatically by some runtime library. That's the goal. So imagine that in a somehow modified Scala or in a language of some kind, we could write these things. So how would we express them? For instance, imagine some keyword like this, define concurrent instead of def, and then we define this function plus in some way as a concurrent function. Now, to make the tuples available, let's have a special function for that called emit. So we emit these values into the concurrent world, and so that makes these values available as concurrent data. So let's say this will be some special method that we need to call on a value, and that somehow makes that value concurrent data. So I like the metaphor of emitting data into the concurrent world. So that's what we will then do. We will define these computations. Now this would be part of the library, so we don't have to define it in our program. This will be part of the language, maybe. But this is our code, and this is our code. So we emit these data items and make them concurrent. But how do we specify that these data items are actually intended for this concurrent function? There's nothing right now that says that. We could have also the times concurrent function, which would also have the same input type. So the type alone is not enough to say that this must be input for this function. And certainly we do not want to write explicitly function calls like this. This defeats the entire purpose of a declarative concurrent language. We don't want to tell the computer how exactly to run the concurrent computation. We gave data and we said that the computation must be concurrent. That should be sufficient. So this can work only if this plus function can somehow find and consume its input data automatically. How can it do that? Well, it can't unless we somehow label this data, especially for this function. So we need to label this concurrent data in some way in order to express the specific connection between this data and this function, so that this data is to be considered input for this function. Well, one way of doing this is to say, well, let's put a label on this data. Let's attach a label to it. And the label, an easy way of doing a label is to just say this name, imp, needs to be the label. And let's do that and write code like this. So we emit this data item, attaching to it the label imp. And imagine now we can implement a runtime system that will monitor emission of things and look at the labels. And if the label is imp and we have defined a concurrent function whose argument is called imp, then the system will know that this data item needs to be given to this concurrent function, And the runtime system can start automatically a new thread on which this function would be evaluated with this data. And the runtime system can do this automatically every time a new data value is emitted with this label. So this seems to be workable now. We have resolved the problem of connecting data to computations. We're coordinating computations. Now, let's not discuss right now that this is a string and that the function argument's name is not a string. So let's ignore this for now. This will be resolved very shortly. But for now, let's just say this is some kind of label type. Now, how could we specify the source of input data for the times function? If we define the times function with an argument whose name is imp, this would be confusing. We would confuse the system. So we need a different name for the times function. Let's call that something else. For example, imp2 or something like this. It doesn't matter, but it needs to be a different name. Okay, so that takes care of the possible confusion between the input data for plus and for times. The problem remains, however, that we still need to specify that this input value imp2 is made out of two parts, each being the output of the computation that was run when we emitted this. So output of this computation. How do we specify that this is to be done? So in order to do that, we just need to think back to what happens when a computation is finished. It computes some value, but what happens to that value? It would be natural if that value were to become available as concurrent data in turn. The input is concurrent data, and the output should also be concurrent data. That is somehow natural if we think about the concept of concurrent function. Concurrent functions are just functions that operate on concurrent data. Now we are trying to make this precise. We're trying to define the operational semantics of what those words actually mean. So the concurrent function consumes the labeled concurrent data as input, and it must emit its result value also as labeled data. What is the label that it should put on the result value? Now this label, in other words, in the function body, there must be a function call like this to emit some result value with some label. What would be the label? The label must be known in the function body, otherwise we won't be able to write that code at all. But in our case, there are two different instances of plus that need to be run, and their return values must carry two different labels. Otherwise, we won't be able to distinguish them and put them into a tuple. Now, you could say the function times is symmetric. It doesn't matter in which order you put them into the tuple. That's true. But there might be other functions that are not symmetric. We don't want to limit ourselves like this. So we must provide the function plus with an output label. It cannot know in advance which run it is. We will emit two data items for it, and the code of this function cannot know which one it is. And so it cannot possibly know which label to put unless we give the label as part of the input data. So let's do that. Let's make the data type that is the input of plus, a triple label, and the two integers that we had before. Then the label can be passed as part of the input value. Let's redefine, and still in our imaginary language, the code will look like this. The plus function will have this input type, and the code would be like this. We will first unpack the input, and then we emit on the output label the resulting expression. The times function, let's make it 2-argument function, and it will, let's just for simplicity, it will print the result. Now we emit the input data, which will look like this. We emit on the label imp data with label imp1. So imp1 is part of the data here, but it will become the label, which will be input for this function. So in this way, we designate and coordinate the concurrent computations. This is the entire concurrent program that we would like to be able to write to express computations like these. This is completely declarative in that we specified the computations we want to do. We specified that they are concurrent. We just said that this must be concurrent, this must be concurrent. And we prepared the data that is labeled for these concurrent computations. And we just expect this to work. The runtime system must examine this definition, realize that there are these concurrent functions that have inputs labeled in this way. The runtime system will wait until some data is emitted into the concurrent world. Then the runtime system will look at the labels that this concurrent data will carry. And if it looks and finds the label imp, it knows that this function needs to be run on a new thread. And if it finds labels imp1 and imp2, then it knows that this function needs to be run on a new thread. And also note, if this concurrent run finishes first with imp2, say, but the concurrent run with imp1 is still running, then this function cannot be run yet, because it requires two inputs labeled with imp1 and imp2. Until we have both of them available in the concurrent world, this function cannot be run. So the runtime system should be able to know that and simply wait until all the inputs are available. And once they are emitted, because this function will emit first one output label with this and then another, once they are emitted, they become available, and the runtime system should realize that and start a new thread with this. Now it's reasonably straightforward to implement such a system. Let's have an overview of what has been achieved with this DSL design. So far, we can declare functions to be concurrent. We can declare data to be concurrent, providing a label. Concurrent functions can automatically find and consume their inputs whenever the inputs are available. Because of this, concurrency and parallelism are automatic and, so to speak, data-driven. If multiple input data is available, then the runtime system can automatically start multiple runs of concurrent functions in parallel. And this is completely safe because the data for these parallel runs are separate items of concurrent data. There's no shared state. We do not need to run any code or to write any code that starts the parallel computations, allocates new threads, stops them, monitors them, performs supervision of any kind. All of that is done automatically by the runtime system. The runtime system can optimize performance without any code that needs to be written by the programmer. It can take care of scheduling, create as many threads as can be created or needed, and optimize the computations in different ways. And that seems to be a very good concurrent language indeed. Let's simplify it a little bit and make it actually work in Scala. So far, this is just pseudocode. This is not real Scala. Let's simplify it, and also let's make it more type safe so that our types are more strongly checked. The first step is that we want to make labels into first-class values, not just some magical names of function arguments and strings here, but actually first-class values. This value should know the type of the data item that it is attached to. Otherwise, we will have typing problems, and we want to use the type system for strong type checking. So imagine that the label would be of some type such as m of a, where m is a class that's parameterized by a type parameter a, and the data items must have type a when we use that label. The chemist library defines the class named m, actually. And, for example, a label could have this type, and then it must be used with data items of type int. Otherwise, it's a type error. To define the labels, we can use the constructor of the class m. Now, this is actual Scala code now, where I have imported the chemist library like this. We define labels imp1 and imp2. This is just a very straightforward and verbose definition that makes it very clear what we're doing. We're creating a new value of class m with type parameter int. There's an argument for the class constructor, which is a string. This argument is for debugging purposes only. It does not affect in any way the semantics of computations. And the chemist library contains a shorter way of defining labels, but this would be the shorter way with a macro called m. But this is not important right now. It's important for us to understand how these improvements in the language help us now to write code. So here's how we would define first-class label values. How do we use them to emit concurrent data into the concurrent world? We just write things like this. Instead of the emit, we use this syntax, which is to say the emit function is called apply in the m class, and so that is shorter than. So in this way, we prevent data of wrong type to be emitted. Labels will enforce the type that they're declared with. how do we define concurrent functions in the syntax of the chemist library? So there is a special syntax. There is no def concur, obviously. And also the names of function arguments have to be represented somehow differently. They have to be connected with these labels that we just defined as first-class values. The way to do that in Scala is to use a case expression where you can use the names you defined here as long as they have an unapply method. This is a technical detail, but the result is that we can write a syntax like this, where this replaces the definition of the function, and this is actually a value. This is not a definition at top level. This is just a value that could be assigned to something like this. It doesn't have to be assigned. It could be used as part of a larger expression if that's what you want. It's just a value. So concurrent functions are values. The syntax replaces the names of the arguments here, or labels as we call them, by these constructor-like syntax symbols, and the plus sign replaces the comma here. Other than that, it's just a syntactic transformation. We define a function that has two inputs. The inputs must be labeled imp1 and imp2. They are both concurrent data. And the body of the function prints this. Concurrent functions cannot have inputs that are non-concurrent. That makes no sense. Concurrent functions must take concurrent data as input, which means one or more of these labels like this, and concurrent functions may return or emit concurrent data back into the concurrent world, but this is not required. We could just do this if that's enough for this example. Note that these labels have been already defined before we can use them. Scala requires us to do that. Otherwise, this code could not possibly compile. So we use the syntax like this, which is shorter, and it means the concurrent data value x labeled by imp1. And these concurrent values are here used in a pattern matching syntax. So x and y are actually pattern variables that are automatically type checked because we have defined the labels imp1 and imp2 with the type int. Let's now define the type concurrent function plus. So concurrent function plus, as we want here in this pseudocode, it needs to have an input type which is a triple, a label and two integers. Let's do that. So we define first a label with that type. So that is the type of the data that a label attached to. It's a triple containing a label of type int and two integers. And then we can define plus. Having defined the input label for it, we define plus. Now the triple can be directly pattern matched. We don't need to write code like we did up here, where we first decomposed the triple and then did computations. We don't need to do that. We can just use Scala's standard pattern matching. So this would be type emit, and these would be integers. The body of this function emits a new item of concurrent data labeled by the output label. Note that the output label is a parameter in this body. So we pass that to this concurrent function. And that was our design. So far, we have defined these as values. This definition alone does not actually start any computations, and it does not enable any computations. These are just declarative descriptions, so to speak, of the logic of our program. So after these definitions, we will have these values in memory, but there won't be any threads created or any computations started. We can't yet use this program. In order to start anything, we would have to emit the input for the plus. Well, recall our plan was to do this. So now in the new syntax, this would mean we emit input with these triples. But actually, we can't emit any input until these definitions are activated in the runtime engine. Since all of this requires a runtime, a special runtime that will actually do the concurrent scheduling, we need to activate these definitions in the concurrent engine. Once we activate it, then the runtime will begin monitoring this input data, but not before. And it's convenient to have this activation step as a separate step in the language, rather than make activation automatic. Making activation automatic was the mistake that Scala designers make with future. Once you define a future value, it's already activated and will be scheduled, which means you cannot define a future value unless you already provide a thread pool for that computation to be scheduled on. This mixes concerns: the concern of describing the program logic of what needs to be computed after what using what data, and the concern of actually scheduling the computations on what thread pool and when to start scheduling them. So let us not repeat that mistake and make the activation into a separate step. Another advantage of doing this would be that we could create a bunch of these values describing concurrent functions and concurrent data and combine them, compose them in different ways. And once we're done composing them, we can pass this to somebody else, to some other part of the program that is responsible for scheduling, for starting. That part of the program would be responsible for managing thread pools and such. In this way, we can separate concerns very cleanly. One part of the program manages logic, another part could assemble smaller parts of logic into larger parts, and finally, a third part of the program that has access to resources and thread pools and so on will decide how to schedule these computations. So without further ado, let's activate our definitions. The activation method in the chemist library is called cite. And it's called like this with a list of declared concurrent functions. That's enough. That's the minimum definition. There are more options, but basically that's the minimum that we need to do. The motivation for calling this method cite rather than activate or something like this. Cite is shorter, but another motivation is that we need to, in some sense, declare a holding place or a holding site for all this concurrent data that's going to be emitted. In the runtime engine, there must be some container, some data structure, where all this emitted data is held while it's waiting to be consumed by concurrent functions. So that place or data structure where this concurrent data is held is called a site or a concurrent site. Now, let's see if this code works. All we need to do now is to emit the input data. So the input data imp with this triple and imp with this triple. That should be it. That should actually run. Let me run this test in IntelliJ and see that it prints 21 when it finishes running. Yes. Let's see how many lines of code we used to declare this computation. 1, 2, 3, 4, 5, 6. We have 6 lines of code to implement this computation. Let's see how many lines of code we used with this computation when we did future. 1, 2, 3, 4, 5. Well, this probably doesn't count. This is a test. If we did it like this, it would be 8 lines rather than 5. So far, our language is doing well enough. Consider the next example. We wanted to have a computation that will process all arriving data items one after another concurrently. So imagine we are receiving some data items carrying double values, x1, x2, and so on. And for each xi, we need to compute some function, some mathematical function, say, such as a cosine. And let's suppose that this function could take a longer time to compute. So we want to do all these computations in parallel. So these items could arrive very quickly, more quickly than we can process them. So we want to process in parallel as much as possible. After this computation is finished, we want to update the running maximum value. So we want to find the maximum of all cosine values of the numbers we're given. To do that, we will keep an updated value, max cos. And so there's a difficulty that these things are going to happen in parallel, but this is a single point where there's only one running max value that needs to take into account all of these results of computations running in parallel. We want to allow max cost to be updated in arbitrary order, because we don't know in what order those would finish. Imagine that these are complicated mathematical computations, not just a cosine. They could take different time depending on x. And so we are computing the max value. It doesn't matter in which order we update it. And so we want to maximize efficiency and allow this value max cost to be updated in arbitrary order. How do we implement such a task? Well, clearly, these x's need to be concurrent data items. So let's assume that some other code will emit them, and we just need to be able to consume them. We will not write code right now that uses this in any other way. We just have code that will emit those x's in some way, and we need to consume them. Now, obviously, they need labels. So each of these x's needs to be labeled as concurrent data. Now, suppose this were the label. Does it make sense to use the same label for all of them? It does, because the computation is the same for all of them. And because these computations need to be run in parallel for all of them. So that's the perfect fit for using the same label for all of these data items. And that's very convenient, very simple. This other code that needs to emit these x's just needs to know this label, which is a value. So this code needs to have that one value, and it can now emit these x's. Therefore, let us define this label first. Now, this is a long definition. As I showed, let's just make it short, because this is how I usually define my labels. The macro m will automatically fill in the debugging name for this label. And usually debugging is not required. There are rare cases when it's required. Certainly not in simple examples like here. Now we need to define the computation. So how shall we do that? So let's try to write code like this. So clearly, the first computation we need to define is the cosine. The cosine consumes a concurrent data item with label x in. It can compute the cosine and put the result into a local variable in the function. But then what? Clearly, this result needs to be emitted as concurrent data. Otherwise, no other concurrent computations would see it. Now that we have decided that this needs to be emitted, we need to have a label for it. Well, we couldn't emit it with the same label, because that would be very confusing. Then we would think this is another input. So we need a different label. Let's define another label for cos output. Let me again simplify this code just to show you how this would be done if you don't need a lot of debugging. Note that this is equivalent to doing this. The m is a macro that automatically fills out the debug name. Debug names are very convenient for DSL debugging, because then you see in the debug output what was the name of the variable you defined in your code. It's very helpful. So that's why I use this functionality. So we have defined the output label. Now we can define the computation for the cosine. It's just going to be cosine emitted with the label x out. Very short code. Nice. So with this code, we have implemented that as the x in data items arrive, they will be consumed in parallel as much as possible. The results of cosine would be emitted as concurrent data items with label x out. And the process will be automatically parallelized, because the runtime does that when you have the same label the same label goes to the same computation, and if there are many threads available, many cores available, that is, the runtime system will optimize across the cores. Now, these concurrent values will be emitted asynchronously at unpredictable times because the input is arriving at unpredictable times and because this computation can take, in principle, different time. If it's so simple as cosine, then probably not so unpredictable, but imagine this is some other more difficult computation. What remains is for us to maintain this max cosine value. Now, how can we do that? We get x out emitted asynchronously at unpredictable times. We can have many of them emitted very quickly. Clearly, the only way to look at them is to have some concurrent function that will consume them. So we can have this max cos updated as part of that concurrent function. But it would be impossible to have max cos updated if it's itself not a concurrent value, because if it's some ordinary value, then we will have a race condition. We might have many instances of the updating function running at the same time, trying to update the max cos. So let's declare max cos as concurrent data, and that will take care of the problem. Here's how. We define a max cos label. We will emit the initial max cos concurrent value. And whenever an x out item is emitted, we will run a concurrent function that will consume it, and also it will consume the max cos. The body of the function will therefore access the value x and the previous value of max cos. We could compute the new max value like this. But then what? Well, clearly we have to emit something. We have to emit the concurrent value of something. We emit this with what label? Well, this value needs to replace the value that was previously emitted with the label max cos. Logically, we just emit the same label max cos with the new value. So this will in effect update the value, although there is no mutation here. We consumed a previous copy of this concurrent data item labeled max cos with value c. We emit a new instance or a new copy of a data item labeled also max cos but with a new value. So there's no mutation. It's logically speaking an update, but actually there is no mutation. These are pure functions that take their input values and produce an output. They emit this new value, new concurrent data item. Now, we can just inline this and write the code for the update function like this, shorter. So, we're finished actually with the main code. Now at any time when a new data item xin arrives, because somebody emitted it in some other place of the code, then first the runtime system will run the do_cos concurrent function that will consume this data item, will emit x out. Then the runtime system will notice that x out is emitted, and it will run this. Now, it will only be able to run this if a max cos were also emitted. So we need to not forget to emit the max cos before we start using this code. Now notice the entire code is just 5 lines. It has obviously no deadlocks, except if we forget to emit max cos at the beginning. That's a very easy mistake to make. Just forget it. I'm planning to do it, but I'm just distracted doing other things, and I forget to write one line of code that emits this concurrent data item, and then nothing ever starts because this update function needs 2 data items to start, and everything just silently waits. That's a very easy mistake to make in this language. So let's try not to make that mistake. And there are ways of preventing this mistake from happening. There are features in the chemist library that helps avoid this kind of mistake. But let's continue. So actually, so far, all we're doing is we're emitting new concurrent data items. We won't ever see anything in a test because all of this will happen on some threads and we won't see these values. So how can we access the value of max cos? How can we read the current value that is existing in the concurrent world under the label max cos? You cannot directly access it from, say, test code. The way to access it is by having a concurrent function. And so inside a concurrent function that consumes this, you can see the value. That's the only way to have access to that value. So in order to read that value, we need to define another concurrent function. Let's define it. Let's call it read max. It will consume max cos and do what? Well, it will have access to this value. So well, it can print it, but that's not so interesting. Also, there's a problem that this function now will be called, possibly, right away when this concurrent data item is available. That's not what we want. What we want is to run this function only when we actually need to read that value, not any time that this value is available. So how do we signal that we want to read that value? The only way to signal anything in our paradigm is to emit an item of concurrent data. So let's define another label, say read, and have that as an additional input of this concurrent function. And then this concurrent function will not run until we emit the read item. Now the read item doesn't have to actually carry any values. It could be just a unit value. And it just serves to signal that we want to read that value. Once we emit this item, this function could run and do something. So for example, we could write a function like this. It will consume max cos, it will consume read, it will print the value of max cos, and it will emit max cos back with unchanged value. So that kind of thing could be useful, say, for logging or debugging. Let's implement a better test rather than just do a side effect. It will be useful if we created an interface between this new concurrent DSL and Scala futures, say. Then we could write a test that waits on a future and reads some value from that future, say. To do that, we just create a Scala promise which is in the standard library. We resolve the promise inside this function body instead of printing. And the promise has a value, which is going to be the C, and that's how we can read the result from outside of this entire concurrent world. So all we need to do is to have a promise somehow passed into this function. So let's put the promise as a value on the read label. We will create a new promise every time and pass it with the read label. Let's define the read label. Again, let me just define it in a simpler way. It's a promise double that is carrying. So this is a data items type, going to be promise of double. And the body of the function is that it takes max cost, it takes the read item, it resolves the promise using the value C, and then it emits back the max cost concurrent data item with unchanged value. So nothing has changed. This is very quick to execute. And we have a handle on this from outside of the concurrent world. In order to read the value, we just create a fresh promise value, put it on a read, emit it, and wait for the future to resolve. Before testing this code, as I said before, we need to activate this entire concurrent world or concurrent site. The site will hold all this concurrent data that we emit, the read, the max cost, and so on. The X in, X out, all of that would be held in this concurrent site. But this is all handled by the runtime. We do not write code for this in our application. All we write is this. We activate the site, and once we have done this, we can begin the test. So let's not forget to emit a concurrent value of max cost. If we don't do this, nothing will ever start. Let's put the initial value to -1, which is safe because cosine is never below -1. So now we can emit some X-ins. So imagine this were the code that emits X-ins, double values from 1 to 10. So we just write standard Scala code for this. There's no special requirement about that code. Or this code could be inside some concurrent function as well. This doesn't matter. As long as somebody calls this label, which has an apply method, so it looks like a function that you call to emit concurrent values. So now after this, the concurrent world will contain one copy of a data item with this label and 10 copies of data items with this label. It will certainly take a bit of time for these 10 computations to run and then 10 updates. So let's sleep half a second and then we will read the value. This is of course brittle. We don't really know that half a second is enough. What if our computer is suddenly very slow and garbage collecting and updating all the software on your user account and so on? We don't know if half a second is really enough. So it's a brittle and a very crude test. But that's okay for now. This is just a test. So after sleeping half a second, let's make a fresh promise with double value, and we emit a data item with the read label carrying that fresh promise. And then we can wait for the future. So this is the future that corresponds to the promise, and we wait for it. Now, I already ran this test. Let me run it again. The 0.96 is the maximum value that it found among the first 10 cosine numbers. Right. The test passed. So here is the second example. Let's see how many lines of code we need to implement it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 lines of code. Together with the interface to the Scala futures, which cost us additional 2 lines of code. So in 9 lines of code, which is quite declarative in the sense that we just describe what we would like done concurrently. We don't describe when to start it, or start 2 of them right now, or anything like this. We just describe there's some bookkeeping, that is the labels. We have to define all these labels before we can use them. But that's about it. So it's cheap to define these labels. There's just small data structures in memory. It's also relatively cheap to define concurrent functions. These are, they occupy a bit of memory, but upfront. But if you have a million parallel instances of running this, that's cheap. That can be done. They're not threads. They don't correspond to threads. They are just functions that are run on a shared thread pool. Now, let me conclude that actually we have finished designing a concurrent language. This is the entire language. We have 3 primitives in the language: a label, which we define, a concurrent function, which we define declaratively, and the site that we also need to activate. Now, we could simplify the language by saying that this is not necessary. All concurrent functions are automatically activated all the time whenever you declare them. This would be, as I explained, a mistake. But this is not a lot of cost. Just 1 line to declare your concurrent functions. And that's actually the 3 primitives with very clear semantics. There's this concurrent data that is being emitted into the concurrent world. It waits there until enough data is there to be consumed by the concurrent functions you declared. So the chemist library actually uses different terminology to describe these primitives and to talk about programs. And this terminology is based on the chemical metaphor. The chemical metaphor is certainly just a metaphor. It's just a way of talking about the same semantics and the same code. This way of talking, however, can be more visually clear than just talking about some concurrent data in a concurrent world. I wanted to show that this language somehow logically follows from first principles, from our desire to write programs where we simply specify that certain computations need to be concurrent and say very little else about how they need to be coordinated. Logically, we derived that we need this concept of labels. The data has to be labeled. But once we introduce this concept, this is just one concept, and it gives us everything. All possible coordination patterns can be now realized. There are no more features, in principle, that we need. Certainly, the chemist library has many other features for convenience or for performance reasons. But this is not features that are necessary in principle to have more power in expressing concurrent computations. So let me conclude this tutorial by describing how the chemical metaphor makes the reasoning about the concurrent code more visually clear. In the chemical metaphor, the runtime, the engine that implements all this parallel scheduling, is called the chemical machine. Concurrent data is called molecules, and concurrent functions are called reactions, as if they're chemical reactions that consume input molecules and produce output molecules. So, for example, this is interpreted as a chemical reaction that takes a molecule max cos and the molecule read, consumes them, and produces a molecule max cos as a result, as a product of the chemical reaction. The values C and P are values carried by the molecules. So we imagine that each molecule carries a value of a certain type on it. So when you emit a molecule into the concurrent world, you must give it a value of that type. That is the metaphor. So instead of saying concurrent data item X having label L, we simply say molecule L of X. So this syntax is used both to emit molecules and to describe the left-hand sides of reactions. So the same syntax is used on the right-hand side and on the left-hand side of reactions. Just like in chemistry, they use the same syntax on both sides of reactions that describes input molecules and output molecules. More verbosely, we could say molecule L, and L is the designation of a molecule or chemical label of a molecule, such as hydrogen, H2 molecule, or something like this. So it's a chemical designation. It's not a string. It's a value, as we have seen. So we can say molecule L carrying value X, or molecule L of X for short. The value L itself is called a molecule emitter because it can be used as a function like this to emit new copies of a molecule, new instances of a molecule with the value. So the chemical metaphor says that reactions consume their input molecules, which is natural to think about. When a reaction starts, it atomically destroys these two molecules, so they are gone. Then there is some process going on, and then a new molecule appears atomically. So this is an atomic process that, so to speak, instantaneously consumes the input molecules. Then it starts some computations, and then it can emit new molecules. This is the semantics of how chemistry works, and this is how the chemical machine works as well. So this is very visual and easy to imagine. Now, the body of a chemical reaction is a function of the values that are carried on the input molecules. And this is also very natural in the syntax because the values carried by the input molecules are pattern variables in the Scala syntax. Very naturally, the function body depends on pattern variables, but there are no global mutable state variables anywhere. Certainly, we can depend on previously defined constants, but there is no shared mutable state. The chemistry doesn't work with shared mutable state. The chemistry is local. Two molecules meet each other and react. They don't know about molecules far away. They cannot communicate with them magically using some shared mutable state. So that is the chemical metaphor. A reaction can consume one or more molecules. Now, in real chemistry, there are some laws about what molecules can react. In here, these are just labels we define. We can define arbitrary labels, and we can define arbitrary reactions that consume them. So, for example, in this program, we defined that max cos is consumed in this reaction, and also max cos is consumed in that reaction. And it's completely up to us. All this chemistry is completely virtual, it's imaginary. And so we can define arbitrary reactions with arbitrary named molecules, according to our convenience and program logic. Another good visualization is that all the emitted molecules are held at some site, which I call a reaction site. And this is a holding place for molecules that are waiting for reactions to begin. They might be waiting because the CPU is busy and threads are busy and you cannot start more computations until some previous computation is finished. Or they may be waiting because a reaction requires several input molecules and not all of them are yet present at the reaction site. So somebody still needs to emit more molecules and then this reaction can start. So for these reasons, it is necessary to have a holding place for molecules to wait. And that's what's implemented by the chemical machine behind the scenes. Another feature is that if enough molecules are available already at the reaction site to start several copies of the same reaction, then the chemical machine will automatically start several instances of the reaction using parallel threads, if threads are available. And this is similar to how chemistry operates. Molecules react to each other, completely concurrently with any other molecules somewhere else that react with each other. They don't wait for each other. They all react concurrently, as long as there is space for them to do so. And they have found their reaction partners, they can react. So the chemical machine tries to simulate that. As long as all reaction partners required by the definition of the reaction, which is this, as long as all the reaction partners are available at the reaction site, the chemical machine will try to start this computation on another thread. Now, of course, if all threads are busy, then this has to wait. But in this way, the programmer doesn't have to worry about this. And as I said, this automatic parallelization is completely safe, because each parallel instance of a reaction will consume a separate set of input data. Separate parallel instances of running this can be started only if we have separate sets of input molecules. So each input molecule will have a different C and a different P here, and so they are completely independent of one another. So another copy of this can run on a different copy of this and a different copy of that, completely independently, in parallel, and completely safely. There is no shared state. So far, we have successfully implemented some very simple concurrent programs. We have seen that this language is very high level, concise, very declarative, in the sense that we say very little else other than what computations we want and which of them are concurrent. The only thing that we need to say beyond that is defining labels for data. So labeling the concurrent data, that serves the purpose of coordinating concurrent computations. So that is still declarative because it doesn't tell the computer when to start them. The runtime will decide that automatically. And so, as we have seen, reactions are pure functions that depend only on the values carried by input molecules. So it's in a sense, it's purely functional concurrent computation. The concurrency is automatic, and all data is passed as labeled message data, so to speak. The word message is not necessary here, but there is already a concept of message passing concurrency that you might be familiar with. And so that is very similar. That is concurrency where data is not obtained from some shared mutable storage, but the data is explicitly passed on messages of some kind, of some separated pieces of data that are consumed separately and created separately. So we don't have to call them messages, and I don't like to call them messages, because messages evoke the idea of a mailbox or a queue of messages, and that's not what happens here. There is no queue. All those items of concurrent data or molecules, they just sit at the reaction site in an unordered bag and wait until they're consumed in arbitrary order. There's no linear queue anywhere in this picture. So this concludes my description of this concurrency language, which I call the chemical machine. In the academic literature, this paradigm is called joint calculus. In my view, this is an unhelpful choice of words. It's not a calculus, it's a programming language, and join does not express what it does. I also do not advise you to read any academic papers or books about joint calculus. Most likely you won't understand what they say, because they are not written with programmers in mind. They're written for other academics. They are not tutorial level papers or books. They do not explain clearly how this concurrency paradigm can be used in practice for actually writing parallel programs. They only consider some theoretical questions, usually, about joint calculus, such as, is this calculus equivalent to some other calculus or not? Now, these questions are completely irrelevant to software development until you understand how to use this paradigm for practical computation. And so instead of reading academic literature, I urge you to read my tutorial, which I'm still working on, but it is largely complete now. It's a tutorial level book-length documentation that explains chemical machine programming using several metaphors like the ones I just used here and many, many examples. In my experience, and I have been working with the chemical machine a little bit over a few years, once you understand how to reason about these molecules and reactions, or concurrent data and concurrent functions, however you want to call them. I prefer to call them molecules and reactions because it's more visual for me. But the concepts are simple enough so that you can easily learn how to reason about it. And then you can systematically derive implementations of concurrency algorithms in a very concise manner. I was surprised how concise the code becomes. It's very, very short. Also, programming in the chemical machine, as I said, is systematic in the sense that you logically derive your program. There's very little you can choose to do. There are very few primitives. There's just reaction and molecule. So whatever you do, it must be either a new molecule or a new reaction having some new molecules. And because there are so few choices for you as a programmer to control a concurrent computation, there's usually just one way of solving a given concurrency problem. And usually you can quickly find that solution by just logical reasoning. I have illustrated this kind of reasoning in the examples shown in this tutorial. Although these examples are very elementary, the same kind of reasoning applies to more complex problems. You just ask, I need to do this, so looks like I need a new reaction. What would be the input molecules for it? The molecules I have are not sufficient. Let me take another one. I can define whatever I want. I can define many new molecules if I need them, just for auxiliary purposes. I can define auxiliary reactions if I need them. Let me try to define this, then let me try to see how that works. Usually, after a few minutes, you're done. You can solve all of those concurrency puzzles using just logical reasoning. Now let me comment briefly on implementation and practical use of this. Certainly this is experimental quality code that I cannot recommend right now for production use. The chemical machine itself is, as I said, very concise. It has very few primitives, and it can be embedded as a library-based DSL in various programming languages. The chemical machine adds only 2 or 3 primitives to the programming language, and so it's quite orthogonal to whatever else the programming language already has. It just adds very specific primitives for concurrency and nothing else. So everything else just is used from the host language, such as functions, pattern matching, types, and so on. If you don't have types, then you cannot check, but you can do the same things. You can still have the same functions called in the same way. The syntax, of course, needs to be designed more carefully. There exist implementations of the chemical machine for several languages, and most of these implementations are a quick one-person effort, because it's not so difficult to have some proof of concept implementation. The only really well-developed implementation is the one for OCaml. But that is a compiler patch. It is not a library. So they're maintaining a compiler patch, changing the language into a language they call JOCaml, and so they compile your concurrent application. Now, OCaml has not a great support for concurrency as such. It might have been improved, but Haskell certainly has a better support as a language. C++, I've seen it in Boost. Somebody put an implementation. So basically, one person can learn this reasonably quickly, understand how the chemical machine should work, and implement it without a lot of work required. So this test uses my implementation in Scala, which is at this URL. I encourage you to take a look at that repository and read the documentation, which I will continue to work on, but right now it's reasonably complete as a tutorial. And finally, what I described is a language for concurrency on a single machine. There is no concept of distributed computation here. There is full support for arbitrary concurrency in this language, but it's limited to a single machine. So the Scala implementation is limited to a single JVM, although it will use all cores on a multi-core machine, and it will be multi-threaded in any case. But in the near future, I hope to develop an extension of this language to enable distributed programming, that is, running programs on a cluster automatically, and also fully declaratively. Just in your code, you would say, this computation is distributed, this data is distributed. Just like we said in the language I showed you, this data is concurrent, this function is concurrent, and that was sufficient with a tiny bit of bookkeeping relating to labels and molecule emitters and such. Labels and molecule emitters are the same thing. So I hope to implement automatic declarative distributed programming in the same way, where you just say, this computation needs to be distributed and this data needs to be distributed. And no more code than that. Just a new keyword or something, or new type for distributed data. And that should be it. If I'm successful, I hope this will be a great way of programming parallel and distributed applications.